Welcome back. In the last lecture, we have discussed a higher dimensional Fourier series for one periodic function. And what we mean by one periodic function in the higher dimension is the following: any function f from R n to C is said to be the vector 1 periodic if f of x plus m, this is equal to f of x for all x belongs to R n and m the nth tuple of integers. And so, like in the case of one dimension, here we would like to relate the Fourier series and the Fourier transform. There we have seen how important the Poisson summation formula was, and towards that end we would like to have an analog of Poisson summation formula in the higher dimension, and we will explore some of its applications. So, first assume f is in the Schwarz space of R n. Because it has a rapid decay, we can define capital F of x, this is equal to summation over m varies over z n f of x plus m. This sum converges because f is in the Schwarz space and it has a very nice decay. Now, what one can show is that f hat for k belongs to z n. You see, this f is one periodic, and then the integral of f over T n this is finite. So, we can talk of the Fourier coefficient of this is equal to e to the power minus 2 pi I k dot x dx. Now, let us plug in the definition of capital F. And because this is absolutely summable series, we can interchange the sum and the integral. So, this becomes m varies over z n, and then this integral is by our definition is nothing but the cube 0 1 f of x plus m e to the power minus 2 pi I k dot x dx, and which is equal to, you see, m is m 1 to m n. Therefore, if I make a change of variable, so we have a sum where each m is equal to m 1 to m n, and m I belongs to z, and then this one becomes product of I from 1 to m, m I plus 1, and then this is f of x e to the power minus 2 pi I k dot x minus of m dx. Now, you can see that here dot is, so this we can write it as summation over m I varies over z I from 1 to n, then this product f of x e to the power minus 2 pi I k dot x into e to the power minus 2 pi I k dot m, this is plus. So, this is dx. Now, this factor is equal to 1, therefore, this if we write it down, this is integral over R n f of x e to the power minus 2 pi I k dot x dx, which is nothing but our Fourier transform of the Schwarz class function f hat of k. And if f is in Schwarz space, therefore, f hat is also in Schwarz space. F in Schwarz space will imply, we have seen that f hat is also in Schwarz space. This will imply that summation over mod of f hat of k, k varies over z n, this is finite. Therefore, by inversion formula, we have f of x, this is equal to summation k varies over z to the power n f hat of k e to the power 2 pi I k dot x. This, in fact, we can write this is m varies over z n f of x plus m, this is equal to summation over m varies over z n f hat of m e to the power 2 pi I m dot x. This is nothing but our Poisson summation formula. In short, we will call it as PSF. Okay. So, now we have got the required Poisson summation formula. Now, what one would like to see some application of this Poisson summation formula. One of the very cute application of Poisson summation formula in dimension 1, that means n equal to 1, we have seen that k from 1 to infinity 1 by k square, this is equal to pi square by 6. We are able to compute the sum precisely 1 by k square by using the Poisson summation formula previously. So, now if we would like to have an analog of this in higher dimension. So, this the natural choice would be summation over. So, this we can rewrite it as summation k varies over z minus 0 and 1 over k square, this is equal to pi square by 3. So, now left hand side the analog would be k varies over z n minus of 0 and then 1 by mod k, and here dimension is 1, the power is k square. So, one would like to get that what is the value of this. So, that should be the analog of 1 over k square here in the higher dimension. Now, to do that, let us recall as we have seen that in the Poisson kernel, it appears the form is that some constant dependent on dimension divided by 1 plus mod x square whole to the power n plus 1 by 2. So, that suggests us this side is we are going to identify with the Poisson kernel, and then by using the Poisson summation formula, we would like to derive an expression for 1 over summation 1 over mod k to the power n plus 1. We have seen that e to the power minus 2 pi mod x xi, this is some C n by 1 plus mod xi square n plus 1 divided by 2. This what we had derived by the subordination principle. And now, if we define p of x, this is equal to this we can define to be p of xi. So, then p epsilon of x, the dilation we are defining that this is p of x by epsilon for epsilon positive. Therefore, from our earlier knowledge, we know that p epsilon hat of xi is p hat of epsilon of x. P hat of epsilon of x is nothing but e to the power minus 2 pi mod x times epsilon from this formula what we have got. And then p, if I write the p epsilon of x, this is equal to 1 by epsilon to the power n C n by 1 plus mod x square by epsilon square n plus 1 by 2. This is equal to 1 by epsilon to the power n C n by epsilon square plus mod x square n plus 1 by 2 multiplied by epsilon to the power n plus 1. So, this is nothing but C n epsilon divided by epsilon square mod of x square n plus 1 divided by 2. So, now both p epsilon and p epsilon hat, they have nice decay. As we can go back to see whatever we have done for the Poisson summation formula, we would like to give a remark here that if both f and f hat satisfies mod of f of x is less or equal to some constant which may depend on the dimension, and 1 plus mod x square n plus 1 by 2 and mod of f hat of x is less or equal to some d prime of n by 1 plus mod x square n plus 1 by 2, then all the proof of the Poisson summation formula will go through for this function, because we can define f, periodized it, and we can take the Fourier series, and then we can arrive at PSF. So, now in our case, both P epsilon and P epsilon hat, they satisfy the appropriate decay condition for Poisson summation formula to hold. Therefore, we can apply Poisson summation formula for this Poisson kernel, and that what it is going to tell us. So, by applying Poisson summation formula, what we have got is that C n summation over m varies over Z n epsilon by epsilon square plus mod m square to the power n plus 1 by 2 is equal to summation over m varies over j p epsilon hat at m, that is nothing but e to the power minus 2 pi mod m times epsilon and e to the power 2 pi I. When I am looking at 0, so this in particular what I am using is that m varies over Z n, p epsilon of m, this is equal to summation m varies over Z n, p epsilon hat at m. So, that is the Fourier series at x is equal to 0. This is what we are using. So, we have this formula. Now, this will imply this is summation over m varies over Z n 1 by epsilon square plus mod m square to the power n plus 1 by 2 is equal to 1 by epsilon into 1 by C n summation over m varies over Z n e to the power minus 2 pi mod m epsilon. Okay. So, we were interested for the sum m not equal to 0. Therefore, what we have got is that m varies over Z n minus of 0, then 1 by epsilon square plus mod m square to the power n plus 1 by 2. This is equal to 1 over epsilon into 1 over C n summation over m varies over Z n e to the power minus 2 pi mod m epsilon, and then 0th term if I am taking it out, then this is going to be 1 by epsilon to the power n. Okay. So, this suggests that if then what we get is that m varies over Z n minus 0, 1 by mod m to the power m plus 1. This is nothing but limit epsilon goes to 0, 1 over epsilon 1 by C n summation m varies over Z n e to the power minus 2 pi mod m epsilon minus 1 by epsilon to the power n. And this limit exists, and that is what is the summation of this. If n is equal to 1, then one can show that the right hand side is nothing but pi square by 3. Therefore, what we have got is that we got a formula for 1 over mod k to the power n plus 1 when k is not equal to 0, in the higher dimension. Okay. So, another next application what we would like to see is that let us we say that x belongs to R n is said to be a lattice point if x is in Z n. So, all those Z n they are the lattice point. So, for example, in R 2, so 1 1 all these 0 1 0, then this is let us say 2 3, all these are the lattice point of this. Now, the question is, suppose if I take a ball of radius r, then how many lattice point is going to have. So, now if I take the grid like this, all the integer points on the x axis and all the integers point on the y axis, if I am taking, and if I take a ball of some radius r, then this r is going to contain how many lattice point, that is the question what we would like to ask ourselves. Can we count all those lattice points, and which is so that is what the problem is. So, now let us formulate this problem in the mathematical term. So, what it happens is that let us take denote B to be the unit ball centered at 0 and the radius 1, and B r, if I am taking the B r to be the ball of radius r, this is the closed, we can take closed, so now if you can see that if a lattice point M is in B r, then if I am dilating it, if M is in B r, then M by r, this is going to be in B. So, we would like to calculate the lattice point of B r. Let us denote the indicator function of B. This is the indicator that means, this is going to take the value 1 if x is in B and 0 if x is not in B, which means on this is going to be 1 if x is here, then chi b of x is 1, if x is there, then it is 0. Okay. So, what we are interested to find? We are interested to find all the lattice point. So, on B r, so which means chi b of M by r. So, how many of these M's they are going to be there inside B r can be given by this number, and which is definitely it is the part of the M by r. So, Poisson summation formula is going to relate to the sum of the Fourier transform. So, we need some kind of decay for the Fourier transform. Okay. So, now what we know that chi of b hat of xi modulus, this is lesser equal to some constant times which is dependent on the dimension 1 plus mod xi square to the power n plus 1 by 2. This we know. I am not going to prove it, but this is what we are kind of assuming that this inequality holds true. Now, what we want to compute this. So, once we have this, then what we can have is that we can have a Poisson summation formula. So, Poisson summation formula is going to show that m varies over Z n of chi of b of m by r. This is equal to m varies over Z n chi of b hat of this is going to be r to the power n, and then this is r of m. This is what is the Poisson summation formula is going to give us. Okay. So, now what we do is we do little bit of analysis here. So, let phi is a continuous smooth function with compact support on R n. Support of phi is contained in the ball of radius half centered at 0, and the integral over phi of x dx, this is equal to 1 on R n. This is what is our phi, and then we define for epsilon greater than 0, we define phi epsilon of x, this is equal to chi of 1 minus epsilon by 2 of b convolution of phi epsilon at x. What is phi epsilon of x? Is the dilation of this 1 by epsilon of n phi of x by epsilon. And similarly, we have psi epsilon of x, this is equal to indicator function of 1 plus epsilon by 2 times b convolution of phi epsilon of x. So, what is so if I have b is here the unit ball, then the radius is we have for an epsilon. So, this ball is 1 minus epsilon by 2 b, and then this ball is 1 plus epsilon by 2 b. Now, using these two functions, so what we are going to get that number of lattice point present in B. So, we will take this up in the next lecture and do the precise calculation to find an estimate of how many lattice point is going to be there inside the ball of radius r. Thank you.